Hello, everyone, and welcome to Building a Software-Defined Network using Kubernetes API machinery and controllers. My name is Matteo Olivi, and I'm a recent computer engineering master's graduate from the University of Bologna. This talk is about a project I worked on while I was an intern at IBM, jointly with my back-then supervisor, Mike Spreitzer. The project is on GitHub, and we hope to contribute it soon to the Kubernetes examples repo. So let's begin by answering the fundamental question, which is, why even building an SDN using Kubernetes API machinery and controller pattern? And the answer is that we wanted to test and demonstrate that those are general enough and good building blocks, not just for Kubernetes, but for other cloud control planes as well. And so we built KOS, or Kubernetes Open vSwitch SDN, Kubernetes because it's built with Kubernetes API machinery and controller pattern, SDN because it manages VXLAN virtual networks, and Open vSwitch because the data plane of the virtual networks is built by configuring Open vSwitch virtual switches. As a warning, KOS is not for production and it only runs on Linux, so it's only a proof of concept. So let's set the agenda before we move forward. We're going to begin with a short background on VXLAN and the Kubernetes controller pattern, and then we're going to dive into the API of KOS, into its architecture, and finally we're going to discuss some technical problems that we had to solve and that we believe have a relevance beyond just our proof of concept SDN. So VXLAN. VXLAN is a protocol for overlaying virtualized Ethernet networks on top of an underlay of IP networks. And it provides isolation between different virtual networks, as well as the illusion to resources within the same virtual network of being located within the same physical network, even though that's not true. And it achieves this via VXLAN encapsulation. So what happens if two communicating parties exchange data and are within the same virtual network is that the packets or Ethernet frames that they exchange will make use of their virtual addresses, but those have no meaning on the underlay network. And so what happens is that transparently their traffic is intercepted and encapsulated into VXLAN packets that will be routed over the underlay network and that will make use of the IP addresses in use on the underlay network rather than the virtual ones. And the problem that KOS solves is that of dynamically configuring VXLAN overlay networks. So next introductory topic, the Kubernetes controller pattern. In Kubernetes, we have API objects, and API objects have two sections, the spec that describes the desired state of the API object, and the status, which is a report on the observed state. And the Kubernetes control plane consists of a series of control loops or controllers, as they're called, that constantly listen for notifications on API objects and react to them by asynchronously processing the API objects. And processing typically begins by reading the desired state of the API object, modifying the real state of the real world to drive it towards the desired state, and then by writing back the new state of the real world into the status of the API object. And these controllers are not built from scratch, but by using standard building blocks, collectively known as API machinery, and by following a more or less standard design pattern known as the Kubernetes controller pattern. And a really important building block is the informer. An informer is an abstraction to receive notifications on all or a subset of API objects of a certain type from the API servers, and it also maintains a local cache with the most recent version of each API object for which a notification was received. And reception of one such notification triggers execution of what's called a notification handler, which is a small function that typically puts a reference to the API object the notification is about in a work queue. And these references are usually the namespace names of the API objects. And references are extracted from the work queue by a pool of worker threads that use them to retrieve the whole API object associated to the reference from the cache of the informer, and then do the actual processing on that API object. Two things are worth mentioning here. The first one is that informers are eventually consistent. So if an API object goes through a sequence of states, there's no guarantee that there will be a notification for each intermediate states. Rather, those might be skipped. And so the resulting behavior is level-based. And second, the work queue provides implicit locking on the references in it. So I don't have time for the details, but what this concretely means is that we have the guarantee that at any given time, there will be at most one worker processing a given object reference. Okay, we've concluded the background. Now we can look at KOS itself. And let's begin by its API. Users interact with KOS just like they do with Kubernetes by creating, updating, and deleting API objects. And KOS defines 3 custom API object types served by custom API servers. And these custom types are the subnet, the network attachment that you'll see abbreviated to NA for the rest of the slides, and the IP lock. We'll talk about IP locks later in the talk. Now let's focus on the first two. And in this slide, you see examples of them. And on the left, you see a subnet API object. And a subnet describes an IPv4 subnet within a VXLAN virtual network. And so its spec has a field called VNI, which contains a unique numeric identifier of the VXLAN virtual network the subnet is part of. And its spec and a subnet spec also has a field which describes the pool of IP addresses allocatable to resources within that subnet. Subnet also have a status field, more on that later. On the right, you see a network attachment API object. And a network attachment describes a network interface within a VXLAN virtual network. And its spec has a subnet field with the name of the subnet API object the network attachment is part of. And the cost control plane will choose an IP address from that subnet and assign it to the network attachment by writing it into its status guest IP field. And the cost control plane will also write other status field of a network attachment, such as the guest MAC field, which stores the virtual MAC address of the network attachment. And it will also write into the status the VNI of the network attachment, which is, again, the unique numeric identifier of the VXLAN virtual network where the network attachment is. So network attachments somehow represents the nodes in a VXLAN overlay network, and so they must be bound and implemented on a node of the underlay network. And so their spec have a node field that contains the name of the underlay network where they will be implemented, and COS further writes the status of network attachments by writing into it the IP address of the underlay node where they're implemented. Finally, notice that VXLAN virtual networks are not explicitly described by API objects, but they're only identified through a unique numeric identifier, which is, again, the VNI. And so for the remainder of this talk, be aware that I will be using the terms VNI and VXLAN virtual network as synonyms. So COS has to implement network attachments, and it does so by assigning to each network attachment a virtual IP address, a virtual MAC address, and by creating for it a Linux network interface on the underlay node of the network attachment. And the network interfaces of different network attachments that are within the same VXLAN virtual network must be able to communicate with each other via VXLAN encapsulation. And so on every underlay node, there's a virtual switch, and COS further implements each network attachment by connecting its network interface to the virtual switch on its underlay node, and by configuring that virtual switch to encapsulate and decapsulate all the traffic that is sent and received from the network interface. And the encapsulation and decapsulation is performed as described by the VXLAN protocol. So we've seen its API. Now we can look at its architecture. Oh, I'm sorry, I'm talking about COS. And it's very similar to Kubernetes architecture. There's a group of custom API servers that serve the custom API objects. And those custom API objects are stored in a dedicated etcd cluster and are implemented by a group of custom controllers that are built not from scratch, but by using the standard Kubernetes API machinery building blocks that I've mentioned before, such as Informer and Work Queue and Worker Threads. And more precisely, there are 3 custom controllers, and you see 2 of them on the top right of this slide, which are the subnet validator and the IPAM controller. Those are singletons, but more on them later. And then on every underlay node, or worker node, as we call them, there's a COS agent called connection agent, which is responsible of implementing the network attachments that are bound to its node in the way I described in the previous slide. And it does so by interacting with a local Open vSwitch daemon. Finally, COS currently gets deployed as a Kubernetes workload. So all of its components, including API servers and etcd, run within pods managed by a Kubernetes cluster via a deployment or a daemon set. However, conceptually, nothing forbids you from deploying COS as a standalone system. So, okay, we've concluded a high-level overview of COS. Now we can discuss some specific technical problems that we had to solve and that we believe have a relevance beyond just COS. And the first problem is that of enforcing an invariant across multiple API objects of the same type. And this arises because remember that we have subnet API objects, and we can have multiple subnets that are within the same VXLAN virtual network. That is perfectly fine. But if that's the case, we want the pool of IP addresses of those subnets to be disjoint. And we also want those subnets to be within the same Kubernetes namespace, just because it's simpler to think about all the resources within the same VXLAN virtual network as being within the same Kubernetes namespace. And so ideally, if existence of a subnet leads to a violation of one of our two invariants, creation of that subnet should fail. And the only way you can get this behavior is by validating subnets before they're actually created, where by created I mean persisted to etcd. And so the validation logic should reside either in the API servers or in a validating webhook. And it would look something like what you see in this slide. So when a subnet S that does not exist yet is validated, you would start by retrieving all the existing subnets in the same VXLAN virtual network as S, and then you would compare them one by one to S, and if at least one conflict is found, creation of S should fail, otherwise it succeeds. And what I mean by conflict is that S and another subnet mutual existence lead to a violation of an invariant, such as, for instance, because their pool of IP addresses overlap. So this is good, but it's not enough. Because when S is validated, it does not exist yet, but is only compared to already existing subnets. So what might go wrong is that two conflicting subnets are created and validated more or less at the same time, so they're validated in parallel. And so when either one of those two conflicting subnets is validated, the other one is not seen because it does not exist yet. And so validation successfully completes for both subnets, which both get created, and so our invariants have been violated. And we didn't find a way to guarantee that this cannot happen in COS. So we did the next best thing, which is, okay, if two or more conflicting subnets ever come to exist, consumers of subnets will use at most one of them and ignore the others. And we achieved this by giving subnets an additional status field called validated, and COS guarantees that if two or more conflicting subnets ever come to exist, at most one of them will have validated equal to true, and that's how consumers will know that that's the subnet that they can use. And we couldn't have validated being written either in the API servers or by a mutating webhook before the subnet is created, because then we would have had the same race condition that I described in the two previous slides. And so we had to introduce a dedicated custom singleton controller, the subnet validator, whose role is that of validating subnets by running the exact same logic that I've shown before, and by writing the status validated field of subnets. And otherwise, the subnet validator is a pretty standard controller. So it uses an informer to be notified of subnets, and it has a work queue and a pool of worker threads. And the reason validation works in the validator and not in the API servers is because of two joint reasons, really. And the first one is that unlike the API server, when the validator validates a subnet, that subnet already exists. And the second reason is that while subnets may be validated in parallel, they're actually created, that is, persisted to etcd sequentially. So if two or more conflicting subnets are created more or less at the same time, one of them is actually created last. And so when the validator validates that second subnet that is created last, we're guaranteed that the first subnet already exists. And so when the validator processes the second subnet, it will see the other conflicting subnet because it was created first. And this will make validation of the second subnet fail, which is exactly what we want. Now, there's one last subtlety that we have to mention, though, about the subnet validator. And the subtlety is that when the validator validates a subnet S, and it retrieves all the other existing subnets in the same VXLAN virtual network as S, it uses a direct list against the API servers. And this might sound odd because remember that the validator has an informer on subnets with a local cache. And so it would be much more efficient to retrieve all the other existing subnets from that informer cache. However, there are edge cases where correctness would be violated. And this slide shows an example. So assume that the validator retrieves subnets not from the API servers with a direct list, but from the cache of its informer. And assume that two conflicting subnets are created more or less at the same time. And also assume that two validators are running at the same time. Now, before I said that the validator is a singleton, and so it's managed by a deployment with a replica field of one, but that is no hard guarantee. There could be short transients, for instance, because of a network partition, when more than one validator is running at the same time. And if this happens, the gist of our problem is that there's no guarantee on the order with which API objects, including subnets, are added to informer caches. So what might go wrong in this scenario is that at the first subnet validator, the first of the two conflicting subnets is added to the informer cache and validated before the second subnet is added to the informer cache. And so the first validator doesn't see the second subnet when validating the first one, and so validation of the first subnet completes successfully. And the problem is that because of the lack of ordering guarantees, things might happen in the opposite order at the second validator. So what might go wrong is that the second subnet might be added to the informer cache and validated by the second validator even before the first subnet is added to its informer cache. And so the second validator validates the first subnet without seeing, and so the second validator validates the second subnet without seeing the first one. And so validation of the second subnet successfully completes. And so we have two conflicting subnets that both have validated equal to true. And the only way we found to avoid this is to make sure that if multiple validators are running, they all get a consistent view of which subnets exist. And that's what using direct lists against the API server ensures at the cost of a worse performance. Okay, we've concluded discussion of the first of our technical problems. The second problem is that we're going to discuss is that of assigning virtual IP addresses to network attachments while avoiding IP collisions. And once again, there's a dedicated singleton custom controller for this, the IPAM controller. And the IPAM controller is in charge of assigning addresses to network attachments, and it keeps an informer on subnets, and it processes each subnet by initializing an in-memory set with all the available IPs from that subnet. And it also has an informer on network attachments, and it initializes and it processes a network attachment by reading the name of its subnet from the spec, using that name to retrieve the in-memory set of available IPs from that subnet. And then it chooses one IP from that set and it assigns it to the network attachment by writing it into that network attachment status. However, if this is the only thing the IPAM controller does, we have a problem. And once again, the source of our problem is that even though the IPAM controller is intended to be a singleton, there's no guarantee that, for instance, because of a network partition, there will never be more IPAM controllers running. And so what might go wrong is that if the IPAM controller, like I've said so far, only chooses an address by looking at its in-memory set of available IPs, what might go wrong is that if two IPAM controllers are running at the same time, they might choose the same IP address and assign it to two different network attachments that are within the same VXLAN virtual network. And so we would have an IP address collision within the same virtual network, which we obviously don't want. And the solution we found to prevent this from happening is to have the IPAM controller attempt to acquire a global lock on an IP address before actually assigning that IP. And the assignment proceeds only if acquisition of the lock is successful. An interesting part is in how the lock is implemented. A lock is implemented as an IP lock custom API object. And an IP lock object represents a lock on a virtual IP address within a VXLAN virtual network. And the interesting part is in its name. So for an IP lock, on a virtual IP address X within a virtual network that has a VNI Y, the name is a unique function of X and Y. So if two IPAM controllers attempted to lock the same IP address, they would attempt to create two IP lock objects that have the same name and that are within the same namespace. And because Kubernetes API forbids naming collisions, creation of one of the two locks would fail, and the IPAM controller that experiences the failure would react by simply choosing another IP address to assign its network to its network attachment. And this way, collisions on IP addresses are avoided. Okay, we're also done discussing the second technical problem. Now we can look at the third and final one. And this is the problem of dynamic filtering in informers. But first we have to understand why we need this. So to recap, on every worker node or underlay node, there's a COS agent called connection agent that is responsible for implementing the local network attachments. That is, the network attachments that are bound to its underlay node. And it implements them by creating for them a Linux network interface and configuring a local Open vSwitch virtual switch. However, if we want those local network attachments to be able to communicate with remote network attachments that are in their own virtual network, that alone is not enough. And so we say that if on a node, there is at least one local network attachment with a VNI-X, VNI-X is relevant to that node. And what this practically means is that a connection agent on a node needs to be notified besides of local network attachment. Oh, I'm sorry, let me take a step back. So the consequence of the fact that the connection agent on a node must implement local network attachments, it means that it must be notified of those local network attachments, and so it has an informer on local network attachments. However, what I was saying is that this informer on local network attachments alone is not enough. And so, as I was saying, if on a node there's at least one local network attachment with a VNIX, we say that VNIX is relevant on that node. And what this practically means is that a connection agent on a node needs to be notified not only of local network attachments, but also of remote network attachments, so on other nodes, so of network attachments on other nodes that have a relevant VNI. And this slide shows the why. So say that we have two network attachments, A and B, that are within the same VXLAN virtual network, and they wanna say that they are on two different nodes. And now say that the network attachment A wants to send data to network attachment B through its network interface. And so A will either send an ARP request or an Ethernet frame to the remote network attachment B. And that ARP request or Ethernet frame will use as the destination, the virtual IP address or the virtual MAC address of B. But those virtual addresses are meaningless on the underlay network. And so what happens is that on A's node, the virtual switch transparently intercepts the sent traffic and encapsulates it into a VXLAN packet that can travel on the underlay network. And so the destination address of this VXLAN packet is not the virtual IP address of the remote network attachment B, but it's the IP address of the underlay node of that remote network attachment B is implemented. And so the consequence is that to properly do the encapsulation and forwarding, the virtual switch on A's node must be able to map the VNI and virtual IP and virtual MAC address of the remote network attachment B to the IP address of the underlay node where that remote network attachment B is implemented. But the virtual switch alone doesn't do anything. So it can only know this mapping if the connection agent on its node, on A's node, has made it aware of its mapping by appropriately configuring it. And so the question becomes, how does the connection agent on A's node know the mapping between B's VNI and virtual addresses to the IP address of the underlay node where B is implemented? And the answer is that, well, this mapping is natively stored only in the API object of the remote network attachment B. And so the bottom line is that the connection agent on A's node, to properly configure the virtual switch on its node, must also be notified of the remote network attachment B, even though that network attachment is remote, like I said. So to recap, we've introduced the notion of relevant VNI with respect to a node, and we've established that to properly configure the virtual switch on its node, a connection agent also needs to be notified of the remote network attachments that have a relevant VNI. And to complicate things, notice that the set of VNIs that are relevant to a node is dynamic. It changes over time. So for instance, if at one time there are no network attachments that have a VNIX on a node, VNIX is not relevant on that node. But as soon as the first network attachment with VNIX on that node is created, VNIX has become relevant on that node. And when all the network attachments that have VNIX on the node are deleted, VNIX ceases to be relevant on that node. So more concretely, our problem is ensuring that a connection agent on a node is notified only of the remote network attachments that have a relevant VNIs and none of the other remote network attachments, because it doesn't care about those. And this is important because we could also say, oh, we're not going to do that. We're just going to keep a unique informer on all remote network attachments, and it will be the connection agent itself that manually filters the remote network attachments on the basis of whether their VNI is relevant or not. But this would never scale, because it would mean that the API servers would have to notify all of the worker nodes of all of the network attachments, even though most of those notifications would never be needed. And so our first question was, since we use informers to receive notifications, and informers support filtering of API objects on which they receive notifications on the basis of the fields of those API objects. So they allow you to express a filter such as, give me notifications for API objects of this type for whom the field X has value Y. Our first question was, can we configure a single informer to only filter in the remote network attachments that have a relevant VNI? And the answer is no, because filters in informers are only static. So you can configure a filter in an informer before you start the informer, but you can never change it afterwards. Whereas what we want is the capability of filtering on the basis of a set of VNI values that, as we've seen, is dynamic, changes over time. And so our question was, how can we synthesize dynamic filtering out of informers with static filtering? And the solution that we found was to have a dedicated informer for each relevant VNI. So if on a node there are P relevant VNIs, the connection agent on that node will have, besides of an informer on local network attachments, one informer for each relevant VNI that specifically filters in on that specific VNI. And as soon as a new VNI becomes relevant, the connection agent starts an informer dedicated to that VNI. And as soon as a VNI ceases to be relevant, the connection agent stops the informer for that VNI. And this ensures efficiency in the delivery of notifications, but it introduces a knowledge problem that you normally don't have in standard Kubernetes controllers. And the problem is that if you think about the Kubernetes controller pattern, when a worker pops a namespace name or an object reference from the queue, it needs to use that namespace name to retrieve the whole API object to process from the cache of an informer. But with our design, there are potentially a lot of informers, one for each relevant VNI. And so worker doesn't know from which informer to retrieve the network attachment that it must process. And so the solution that we found was to simply have each connection agent maintain an in-memory map that associates each namespace name to the informers where the network attachment that has that namespace name is stored. And this way, a worker that pops a namespace name from the work queue begins by consulting this map, and this way it learns from which informer to retrieve the network attachment that it must process. And entries are added and removed to and from the map by informer notification handlers. So for instance, when there's a creation notification for a network attachment, for a remote network attachment at the informer for VNI X, the creation notification handler will update the map by adding the entry saying that the namespace name of the network attachment the notification is about must be used to retrieve the network attachment at the informer for VNI X. And when that same network attachment is deleted and the deletion notification handler executes, that deletion notification handler will remove the entry from the map. Now, this works, but there's one subtlety that we have to be careful with. And the subtlety arises because there could be transients during which the same network attachment is stored at the same time into more than one informer cache. This problem arises because, like any other API object, network attachments can be updated, but as a result of these updates, their VNI, their virtual network, can change. So let's see an example to better understand. Say that on a node, there are two relevant VNIs, X and Y, and so on that node, there are two informers, besides the one for local network attachments, one for the remote network attachments that have VNI X, and one for the remote network attachments that have VNI Y. Now say that a network attachment that is remote with respect to the node in our example is created and it initially has VNI X, and say that later it is updated and its VNI becomes Y. So for this network attachment, 3 notifications will be received at the node in our example. First, there will be a creation notification at the informer for VNI X, because that was the first VNI of the network attachment. And then when the VNI of the network attachment changes from X to Y, there will be 2 notifications. First, there will be a delete notification for the network attachment at the informer for VNI X that will remove the network attachment from that informer cache, because X is no longer the VNI of our network attachment. And then there will be a creation notification at the informer for VNI Y, which adds the network attachment to the cache of that informer, because that's the new VNI of the network attachment. But the problem is that the problem is that these 3 notifications are delivered to 2 different informers, and there's no guarantee on the order with which notifications are delivered to two different informers. And so what might go wrong is that out of the 3 notifications, the last one to be received is not the creation notification for the new VNI of the network attachment, but is the deletion notification for the old VNI of the network attachment X. And so if this happens, the 2 first notifications that are received are the 2 creation notifications at the informer for VNI X and at the informer for VNI Y. And if this happens, it means that before the last deletion notification is received, the network attachment in our example is stored at the same time into 2 different informers, the one for VNI X and the one for VNI Y. And so if a worker pops the namespace name of the network attachment in our example during this transient, when that worker reads the map from namespace name to informers, it finds out that the map is ambiguous, that it points to 2 different informers at the same time. And so the worker doesn't know what's the informer that contains the network attachment which it should process. And we found that for a worker that is in this situation, it's enough to simply drop the namespace name that it has popped and give up on processing that network attachment. And so a worker in this situation simply pops a new namespace name and moves on to processing another network attachment. And the reason this works is that, remember that informers are eventually consistent, and so eventually we're guaranteed that at the informer for VNIX, the old VNI of the network attachment, a deletion notification for the network attachment will be received. And when that deletion notification is received after some time, the deletion notification handler will remove from the map from namespace name to informers the information that the network attachment in our example is stored at the informer for VNIX because it's no longer there. And it will re-add to the queue the namespace name of that network attachment. And so a new worker will pop that namespace name from the queue. And when that new worker consults the map from namespace name to informers, all the ambiguity will have disappeared. The map will univocally point it to the informer for VNIY. And so the worker will be able to complete processing of the network attachment. Okay, so this concludes discussion of the last technical problem that we had to solve and also concludes my talk. So in summary, we prototyped an SDN using Kubernetes API machinery and controller pattern to test and demonstrate that those are good and general enough building blocks, not just for Kubernetes, but for other cloud control planes as well. And in the process, 3 interesting challenges emerged, and we had to be creative to find solutions to them. But we believe that both those challenges themselves and our solution have a relevance beyond just cost. And so this is it. So I thank you very much for your attention. And if you have any questions, I'll do my best to answer them either now if we have time, or you can email me or send me a DM on Slack. Thank you very much. Hi, everyone. Like I just said in the pre-recorded talk, if you have any questions, feel free to ask them in the Q&A box. We have a couple of minutes left. Okay. So Rakib Mahmoud just asked if the slides are available somewhere. And the answer is yes, the slides are available on the SCAD page of my talk. And after this, I'll make sure to post them on the Slack channel dedicated to the extending Kubernetes track. And before that question, Adriano Pizzuto asked if we have actually implemented the last controller we talked about, which is the connection agent, the one with multiple informers. And the answer is yes, we implemented it, and it's on GitHub open source. I'll make sure to post a link to it on Slack after the Q&A. Okay, Vyacheslav Gorbatik, sorry if I mispronounce your name, asked, could you please once more point the problem which virtual networks help to solve? Sure. So the sort of problem that cost solved is that, again, of implementing and configuring VXLAN virtual network. which are essentially virtualized Ethernet networks that communicate via encapsulation on top of an underlay of IP networks. And those different virtual networks are typically isolated. So the resources within a given virtual network can communicate with other resources within the same VXLAN virtual network, but not with those on other VXLAN virtual networks. And you can have, this is what VXLAN does, and you can have multiple use cases for this, of course. One really big use case is that of implementing multi-tenancy in a cloud data center. So the idea, let me adjust the angle of the camera, sorry. So the idea would be that if you have multiple tenants in a cloud data center, you basically want to give each tenant the abstraction of having his or her own dedicated virtual private cloud. And a really sort of at the bare bone, a way to implement this would be via a VXLAN virtual network. So that could be a use case. This way, each separate tenant would be isolated from the others. And another characteristic of VXLAN, which makes it suitable for cloud data centers, is that it's very scalable in terms of the number of different virtual networks you can support. I don't remember the precise number. I believe it's 16 mega different virtual networks, which, again, obviously is really desirable if you want to implement a cloud data center where you potentially have a lot of different tenants. So Christopher Galds asks, do you have plans to continue your work on this project, eventually taking it to production? And if this is the case, have you put any thought into where the cluster that runs the operator would live? Okay, so yes, we don't consider, me and the other author, don't consider this project to be complete. As I said, the other author was my supervisor while I was an intern at IBM, and we worked on this. We've been also working on this since I got back, although not at a very sort of satisfying rhythm, because we also have other things to do, obviously. But yes, although at a slower pace, we're still working on it. What we have no plan to make it a production system so far. Although if you're interested in that, by all means, let us know. As you know, it's on GitHub, it's open source. One thing which we want to do, which is missing, is do a performance study of the system. And so we would like to sort of characterize the time it takes to actually implement network attachments and metrics like this via a model. And we're planning to do this study at a reasonably high scale, but we are still working on that. Okay, I'm told that time is running out. So I really thank you for your interest. And if you have other questions which I could not answer, just write them on Slack, on the Slack channel on the CNCF workspace dedicated to the Extend Kubernetes track. Okay, thank you very much for your attention, and I'll see you on Slack. Bye.